Oh, so looks like we're winding down to the end of the chapter questions. This is the second to last one, and we're going to have to visit some of our old friends. Use the Lamar formula P equal mu naught Q squared A squared over 6 pi C and special relativity to derive the Leonard formula P equal mu naught Q squared gamma to the sixth over 6 pi C times A squared minus magnitude V cross A over C squared, and then close the parentheses. Clearly, we're going to have to deal with some dot products, cross products, and gammas are going to be afloat. Let's be careful with bookkeeping and see what we have. All right, so in our solution, what we need to understand is that what we need to know that the proper power transforms as a zeroth component of a 4-vector k naught. So k sub or k0, which of course when we discussed this was 1 over c, and this was again if it's the power then it's dw over d tau. And the Lamar formula says that for v equals 0, we have the power dw d tau is equal to 1 over 4 pi epsilon naught 2/3 q squared c cubed a squared. Okay, so that was back in the original formulation of the Lamar formula. And so what we need to do is be careful about this because it's a squared is actually a dot product to a and a. So we're going to have to be careful with how relativity uses 4 vectors and things of that nature. So what we can do is what we need to do is think of a 4 vector whose 0th component reduces to this when the velocity is 0. Okay, well, a squared smells like the a to the nu alpha nu alpha nu. So the 4 vector dot product. But we know that we're going to have to be careful with that because you have the covariant and contravariant 4 vectors, and we're going to have to change up the signage on it. So we're going to have to be careful. So how do we get a 4 vector in here? How about the velocity 4 vector, or the proper velocity 4 vector, a to nu, or a to mu, whose 0th component is just c? Okay, that would make sense. So when v equals 0, of course. So when this is the case, then let's try plugging this in. So k to the mu is equal to 1 over c dw d tau. Again, tau being the proper time here. We got to be careful with all our definitions again. So if we plug this in from the Lamar formula when v equals 0, we get this consideration here, and then this a squared is a dot product, and we can write the dot product of 2 4 vectors with the alpha nu, contravariant, covariant, and then of course we can get the again for the 0th component we can get the c in there via the eta mu, and then of course divide by c. And so what we're going to have to do now is use a lot of algebra and the relativity rules to simplify this. So let's go ahead and dive through. All right, so if that's the case, what we see here is that this reduces to everything, all the constants are the same, except now we have a c to the 5th, and we still have the 4 vector dot product here. And then of course for eta mu, here we just got to be careful because by changing the indice, we have to change the sign on the 0th component. That's just the rules. But with that, let's go ahead and talk about how this works. So this has the right transformation properties, but we must check that it does reduce to the Lamar formula when v equals 0. So let's go ahead and test this. We see that we have dw dt is equal to 1 over gamma dw d tau for proper, and of course we saw that this was equal to k to the 0th component, which was c k0. So everything's working through. With this being said, we get a c canceling with the c's. Cool. The 4 and 2 cancel, and then we're left with a 2 times a 3, which gives us 6. Gamma cancels whenever we plug in the 0th component to eta, which is c gamma. So we have another factor of gamma or another factor of c that cancels. So we're at c to the fourth here. Now we're to c to the fifth cancels to c to the fourth. We split up the fourth into a square and a square, and that cancels down. We like that, so we're left with a c left over after this cancellation. This c squared goes to a mu naught squared, epsilon squared, so the epsilon naughts cancel. We're left with mu squared q squared, or mu naught q squared over 6 pi c over alpha nu alpha nu. Alright, cool. We like that. Easy enough to deal with. Okay, so we are here where we need to be, but now we actually have to do some more work. So, incidentally, this tells us that the power itself, as opposed to the proper power, is a scalar. If this had been obvious from the start, we would simply have looked for a Lorentz scalar that generalizes to the Lamar formula. Excuse me. So with a little more work, and we can reference the results of problem 12.39, particularly the result B, where we calculated what this dot product was, the alpha nu in terms of the ordinary velocity and the acceleration. What we see is that this 4-vector dot product gives us the gamma to the fourth and all this fun junk inside, which is v dot a squared and then c squared minus v squared plus a squared. Cool enough. Again, this is just the results of how the 4 vectors work and how we can combine everything we need to. But do take in mind that we have to be very careful in simplifying. Here we do the force factor on the c squared. So we take that 1 and then we put a c squared under the v. And of course we do this for obvious reasons because we're trying to get this to look like the Lorentz factor. Here, what we do is on the a squared term, we multiply by 1 in the form of gamma squared over gamma squared. So now we could factor out a gamma squared from both of them, hence we get a gamma to the sixth. So what we're left with is a squared over gamma squared plus c, or 1 over c squared v times a squared. And of course, we can plug in the definition for gamma squared here by the a term. So all we did was some clever trickery and maneuvering. With this, now we distribute it. So you see we did that here. We still have a dot product there. But now we could factor out everything that has a 1 over c squared term. So that's these two later terms. And we factor out a -2. So the dot product is the negative sign on it. Now what this actually looks like is we have a component minus another component, which if we generalize this to 4 dimensions looks like a cross product. So now that we have something in this form where we have a square minus something else, cross products and their signs are always gross, kind of nasty, so let's kind of force this thing through. So after some clever manipulation in hindsight, what we say is that v dot a is equal to va cosine theta, where theta is the angle between v and a. No biggie, we've seen this before. So what we're actually trying to say here is that if that's the case, a squared v squared minus v dot a squared, well, let's plug in the definition of the dot product. So a squared v squared minus, plug it in, square everything. We get a v squared a squared because we can change the order there. Then a v squared a squared cosine squared. But now you see that we have a v squared and a squared that we could factor out, and we do that here. Okay, and then we're left with a 1 minus cosine squared theta. But via Pythagorean identity, that's equal to cosine or sine squared theta. But this looks like the magnitude of a cross product squared. So VA sine theta is the magnitude of a cross product, so hence we write V cross A, and of course square it. Thus, the the 4-vector product here of something in itself is equal to gamma to the sixth, a squared minus 1 over c squared with this cross product. That's pretty darn cool. And of course, the c squared we can move in, it's positive, it's square, so move it in, no biggie. So what we actually showed is that the Lamar formula can indeed go to the Lennard formula, and that is just a fascinating result. Of course, the Lamar formula is more readily used and available for us when we have v equals 0, because then that other term goes bye-bye, and we like to see that go bye-bye. But nonetheless, it is still a pain to get here. It's a pain to deal with, but we like what special relativity does, and we like using relativistic regimes because they offer us a perspective that was not available to us before, and that's where the power is. So with that, I'll see you for the last question, and yeah, then we'll start our next journey. Later.